Hello, this is Unit 3, Lesson 9, Optimization. So go ahead and try the warm-up. Okay, so number 1, we're finding the first derivative. So number 1 is going to be the quotient rule. Okay, so we get f prime of x equals derivative of the top, which is e to the 2x times the derivative of 2x, which is 2, times the bottom, x squared minus 3x, minus the derivative of the bottom, 2x minus 3, times the top, all over the bottom squared. Okay, B, we're going to have to do product rule as well as chain rule here, so let's try that. So we have derivative of the first, cosine x, times the second, 5x to the fourth minus 1 to the third, plus derivative of the second, 3 times 5x to the fourth minus 1 squared. Derivative of the inside is 20x to the third times the first, sine of x. Okay, number 2, find the limits. So when we look at A, we can try plugging in the negative 3. So let's do that. So when we plug in the negative 3, we're going to get negative 27 plus 12 plus 15 over 9 plus 3 minus 12. That's 0 over 0. So we can use L'Hopital's rule. So we have limit as t approaches negative 3. We're going to do the derivative of the top, 3t squared minus 4, over the derivative of the bottom, 2t minus 1. Okay, now we're going to try plugging in the negative 3 again. So this gives us 27 minus 4 over negative 6 minus 1. So that's 23 over negative 7. Okay, for B, when we plug in the 0, we get 0 minus 0 over 0. So we have 0 over 0. We can do L'Hopital's, or we can split this up into 2 fractions and use the fact that sine of x over x as x approaches 0 equals 1. So it's kind of your own choice on that. I'm going to go ahead and do L'Hopital's. I think it's just a little bit easier on this one. So I'm going to do limit as x approaches 0. On the top, the derivative is 2 minus cosine 3x times the derivative of 3x, which is 3. On the bottom, the derivative is 1. So now when I plug in 0, cosine of 0 is 1. So I get 2 minus 3 over 1, which is negative 1. All right, today we're doing optimization problems. So solving applied optimization problems, here's our strategies. First, we're going to read the problem until we understand it, sometimes multiple times. We want to think about what are we given and what is the unknown that we're trying to optimize. So optimize means either make it the biggest or smallest it can be. Next, we're going to try to draw a picture, label anything that we know. We're going to introduce variables of things that we don't understand or things that can change. We're going to write an equation for the unknown quantity, relating everything together, and then we're going to test critical points and endpoints in the domain of the unknown, and we're going to try to find our maxes and our mins. So these are kind of similar to the related rates problems that we did. I think they are a bit easier than the related rates. So basically, we are going to apply our strategy when we were finding maxes and mins, extreme values. We would always take our derivative, set it equal to 0, okay? So what that would do is we would take our derivative, set it equal to 0. When we set it equal to 0, we're finding the maximum values or the minimum values, right? So what this does is when we do this in a word problem, we're finding the highest or the lowest values, which is what we're looking for, optimizing things. All right, let's look at some examples. So let's look at number 1. It says an open top box is to be made by cutting small congruent squares from the corners of a 12-inch by 12-inch sheet of tin and bending up the sides. How large should the squares cut from the corners be to make the box hold as much as possible? Okay, so let's just read it one more time. An open top box is to be made by cutting small congruent squares from the corners of a 12 by 12 inch sheet of tin and bending up the sides. How large should the squares cut from the corners be to make the box hold as much as possible? All right, so we're going to go ahead and draw a picture. We have a 12 by 12 inch piece of tin. We are going to cut out of the sides little squares. And what that's going to do is then when we fold up everything, it makes a box. So we are trying to figure out how big to cut these little notches. So we're going to call that X. Okay, and they're all the same, X, 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 all of them. Okay, what are we trying to optimize? It says the box hold as much as possible. That means it's the volume. Okay, we're trying to maximize the volume, length times width times height. All right, so before I get started, I'm just going to draw the picture of what this would actually look like when I fold up the sides. Okay, so I'm going to have this box. Okay, so now let's think about what each of these dimensions would be. Okay, so let's start with this side right here. So this would be like maybe this when I fold that up, okay? So the length of it would be the 12 minus the 2 x's that I'm taking off of the length. So 12 minus 2x. All right, on the other side here, it's going to be the exact same thing. 12 minus 2x. And then the height of the box, when I fold these up, is going to be the x value that I have. All right, so now I can plug those in for my length, width, and height. So I get 12 minus 2x squared times x. Length times width times height. Okay, since I want to optimize the volume, I want to do the first derivative, set it equal to 0. It's going to give me all of my values where the volume is either a high point, a max, or a low point, a min. You can go ahead and use chain and product rule. What I chose to do is actually distribute this all out. Okay, so I'm going to do that. So when I distribute out the 12 minus 2x squared, I get 144 minus 48x plus 4x squared times x. Bring the x in. Okay. Now I'm going to go ahead and do my derivative. So v prime equals, I get 144 minus 96x plus 12x squared. And I want this set equal to 0. Okay, when I do that, I'm going to go ahead and factor out a 12. Okay, the 12 does not help me in terms of trying to equal 0. Okay, so that's kind of just out of there. And so now I'm just going to factor what I have here, the quadratic. I know I'm going to have an x and an x. 6 and 2 would work to equal 12 and add up to negative 8. So my two solutions are 6 and 2. All right, so what this means is that the length 6 and 2, I have extreme values, maxes or mins. So now I'm going to actually go ahead and plug these in to my volume formula to see which one is actually going to give me the maximum volume. Okay, so let's try the 6. So I'm going to plug that into my original volume formula. Okay, so this actually gives me 0 squared times 6, which is 0. Okay, so that's not going to be it. Let's try the other one. Plugging in 2. Okay, so 12 minus 4 is 8. That's 64 times 6, 384. Okay, so that's definitely going to be the maximum. So I'm going to go ahead and write down my final answer. How large should the squares cut from the corners be to make the box hold as much as possible? The squares should be 2 inches by 2 inches to maximize the volume. All right, done with number 1. Go ahead and pause it if you need more time. I'm going to erase and we'll move on to number 2. All right, so number 2, you've been asked to design a 1-liter can shaped like a right circular cylinder. What dimensions will use the least material? Okay, so we have 2 things going on here. When it says 1 liter, that is referring to the volume of the can. Okay, so I know that the volume of the can is 1 liter. And then we want to use the least amount of material. So that's talking about the surface area of the can. Okay? All right, so let's start by writing down our equation for the surface area. Okay, so surface area. We're going to have the area of the top and the area of the bottom. Okay, so the area of the top is the area of that circle, so pi r squared. I want a top and a bottom, so 2 pi r squared, that's the top and the bottom, plus. For the side, think about if I unrolled this can, it makes like a rectangle, where h is this side of the rectangle. The top of the rectangle is the circumference of the circle, so that's going to be 2 pi r. Okay, remember circumference is pi d or 2 pi r. So my area of that is 2 pi r h. Okay, so when I write this all down, I'm noticing I have 2 variables. I have an r and I have an h. So I don't want that. I want 1 variable, and that's where our volume of 1 liter is going to come in, because that allows us to relate the radius and the height to each other, and then we can solve for 1 and plug it in. Okay, so I noticed that I have 1 liter. Liter is a volume. So since I'm looking for the length of the height and the radius, I actually want to use 1,000 cubic centimeters. Those are equivalent. So 1 liter is actually equal to 1,000 centimeters cubed. So since I'm in the end looking for the height and the radius, I want to use the 1,000. Okay, so let's go down here. Volume. Volume of a cylinder would be pi r squared h. It's the area of the circle times the height. And then I'm going to go ahead and divide both sides by pi r squared. So that gives me the height in terms of the radius, and now I can plug that in here. Okay, that's kind of nice because my pi's cancel, and one of my radiuses also cancels. Okay, so I have 2 pi r squared plus 2,000 over r. Okay, now I'm going to go ahead and do my derivative. That's going to optimize my surface area. So I have surface area derivative equals 4 pi r. The 2,000 over r, think of that as 2,000 r to the negative 1. So I get negative 2,000 r to the negative 2, like that. Okay. All right, I want to set this equal to 0. So I'm going to do that. I'm going to add the 2,000 over r squared to the other side. Okay, and then I can cross multiply. So 2,000 equals 4 pi r cubed, divide by 4 pi. and take the cube root. I can't fit it. There we go. Okay, if you put that in your calculator, 2,000 divided by 4 pi, cube root, you get r is approximately, since we're rounding, 5.42. Okay, and then you're going to go ahead and plug in the 5.42 for the height over here into this formula to find the height. Plug in your r, and we get 10.84. All right. So for homework, you guys have 2 of these problems. These are pretty simple problems, okay? Just graph, or sorry, not graph. Just draw a picture, use the strategies that we talked about. One thing that I do want to mention on number 2, 2 sides of a triangle have lengths A and B. Those are fixed, even though that they're letters, and I know we're used to letters being variables, meaning they change. These 2 things are actually constants, okay? They're not changing. So just remember that when you go to do your derivative, that those are constants, okay? Meaning you don't have to use product rule. You can just kind of leave them as coefficients on the problem.